we are looking at modern climate change. We looked at the context, we looked at the forcings, we looked at the radiation forcing associated with the greenhouse gas increases, land use change, and we have slowly moved into looking at specific signals that are there. We haven't said anything about how do we know whether that's anthropogenic or not, but when we looked at the forcing, we have essentially emphasized that the increases are beyond anything that is in a natural range, especially compared to the last 1,000 years or the last millennium. This particular figure again shows the warming or the temperature anomalies with respect to the modern climate period, which we defined somewhat arbitrarily as 1961 to 1990. You can move this window, it doesn't make too much difference. So essentially we were, when we came out of just started the industrial revolution, we were cooler than the present climate, not surprising. And since the 50s, especially after the 1970s, we have warmed rapidly, but the question is that natural variability and things like El Nino and volcanic eruptions will create dips and rapid rises in the overall warming that is happening. So the question that I mentioned several times, that maybe there is a little bit of a flattening of the warming in the last, let's say from 1998 to about 2014 or so. 2015 was a big El Nino, and big El Ninos always spike the temperature, so we have to always keep that in mind. There was a big series, a large number of papers arguing that this flattening of warming was a global warming pause. And then there was a big debate about what caused the pause and whether this really was a pause and so on. And statistically, you can see that there is a bit of a change. So if you think of this as increasing, then there is a bit of a flattening there. And one of the theories that came out earlier was to use the models to show that the character of the El Nino had changed since the last big one before 2015, which was 97-98. That was one of the largest El Ninos recorded in instrumental history. Since then, the El Ninos were slightly different in the sense, unlike the so-called canonical El Ninos, where the warming was happening in the east and along the coast. The warming for the past several El Ninos before 2015 was more around the dateline and the central Pacific, so in this region, and this region remained actually cooler than normal. So this is called the central Pacific or dateline El Nino, and that comes with the fact that the eastern Pacific remains cooler than normal, which obviously makes our whole theory a little bit different. We said when warming happens here, the cooling here together change the sea surface temperature gradient. They feed back to the original wind change, the upwelling, and there is a feedback between wind change, upwelling, SST change, SST gradient from the east to west, and then back to the wind change and so on. Whereas this gradient change is obviously, but much more importantly, we said that when the ocean is dynamically bringing up by upwelling these cold waters, it is soaking up heat from the atmosphere. So the global warming is modulated because of this soaking up of the heat by the ocean. Obviously, if this remains cold for 15-20 years, that should begin to appear as a flattening of the temperature gradient. So that made sense. Since then, there have been many other details that have been found out. So it is now realized that the excess heat from the Pacific was in fact being pushed into the Indian Ocean. And there is also some new data that claims that the Arctic warming was not effectively included in some of these calculations. So maybe the flattening was not as strong as it appears here. Nonetheless, these are kind of the internal variabilities that modulate global warming. That should be the main point you can emphasize to the students, that the global warming happen on top of the natural variability. And the critical question, as I said before, is whether the change in the El Nino itself is related to global warming. It is not clear yet because such El Niños have happened before. It's not that every El Niño looked like this. In fact, since 1980s, many of the El Niños looked a little bit more like this. So these have to be looked at more carefully. If you have data on El Niños, then you can see if El Niño has different flavors. Like this is called the canonical or East Pacific El Niño, this is called the dateline El Niño, and whether these are natural variability of the El Niño. So El Niño itself is a mode of natural variability or internal variability, but the El Niño need not look the same every time, and it can occur in bunches. So in some decades there can be more El Niños, in some decades there can be fewer El Niños. In addition, there can be these changes in the feature in which the warming happens and so on. And it turns out that if the warming happens here, the Indian Ocean drought is stronger than when the warming is here. So even the teleconnections of the El Niño will change. I used the new word teleconnection, which we will come back to, but there is a separate module on El Niño that you can look up. So let's to how do we know this is related to human activities or anthropogenic forcing. Anthropogenic is a word that you will hear all the time, basically means human created, and so this is showing temperatures for the 20th century and into the 21st century, anomalies again with respect to the 1961 to 1990 period. And the thick black line here is what has been observed. It is the average of all the observations, temperature stations that we have been looking at. And there are also the volcanic eruptions shown here, the last big one being Pinatubo. And you can see that the observed variability has ups and downs, which we have been calling as natural variability or volcanic forcing. The red line and these yellow lines are different models simulating the same period using all the forcing, including solar variability, volcanic forcing, and of course top of the atmosphere shortwave radiation. So you have an ocean model, an atmosphere model, a land model. It has some representation of vegetation, some representation of ocean ice. Nowadays the models also have land ice, ice sheets, and so on. The previous generations in the 80s and early 90s, the ice models were not ready, so they used to prescribe that from observations or just prescribe the temperatures and so on. So they were not as accurate in the feedbacks as the newer models are. Nonetheless, the main message is that the models are able to essentially capture the observed warming that happened over the 20th century. This is a way to build confidence, saying the models are able to capture some of the natural variability as well as the trend. And you can see that there are times when the natural variability is not as strongly captured by the models, because the models are some initial condition over land, ocean, and atmosphere, and including greenhouse gases, and then the greenhouse gases are also prescribed as increased by fossil fuel burning. But the models, even though they produce El Niños, monsoons, Pacific decadal oscillation, North Atlantic oscillation, and so on, they need not occur at the same time. So in the 20th century, if the observations have 20 El Niños, the models may have 25 or 15. These are called model biases. But the main point is that given the external forcing in terms of solar variability, volcanoes, and greenhouse gases, the models are able to reproduce the observed trend, the observed warming, which is the most critical thing we are looking for. Of course, we have to understand the biases in internal variability, which has to be taken into account not only for interpreting the warming but also for future projections. But once you have a fairly reliable set of models that produce, the models differ from each other in terms of how they do the radiation model, what kind of grid size they use the finer grid size produces better solution, but it takes more computing time. Some have larger grid size, so they are a little bit less accurate. Their ITCZ is not as sharp, and so on and so forth. Okay. So, what you can do after you have a set of models that are doing a reasonable simulation of the trend is you take out all the man-made forcing like greenhouse gas. So, you fix the greenhouse gases to, let us say, the pre-industrial level, and then see what would be warming if we did not have this increase in greenhouse gases and this additional anthropogenic radiative forcing. And sure enough, you see that here is the observed warming again, and here are all the same model sets being simulated with no anthropogenic forcing. Sure enough, the warming disappears. We cannot do this from observations because the observations have the forcing of the anthropogenic contributions already in them, but it is easy enough to take them out and see where the world would have been if we had not been emitting carbon dioxide, methane, nitrous oxide, changing land use, and so on and so forth. So, this is a clear indication that we have detected a warming. So, detection is very clear. We will see evidences that multiple signals of anthropogenic activities are detected, as I said, in land, atmosphere, ocean, biosphere, hydrosphere, and ecosystems, and so on. And this is called attribution. So, basically we can use this method to say with confidence that the observed warming over the 20th century is directly related to increased greenhouse gases related to human activities. That is a good way to start the understanding of what are human contributions to global warming. So, this is showing the same kind of model simulations now with observations in black lines, and there are times when we have more confidence than other times where data is sparse and so on. But the point is that no matter where you look in on the planet, the range of warming is significant and above the natural variability range from the previous millennium. And when you take out the anthropogenic forcing, other than a few regions, pretty much everywhere else, the anthropogenic forcing contributes to observed global warming. So, if the blue line is not as high as the purple and the black lines, that means the observed response is much larger than the natural response, and this is related to anthropogenic contributions to radiative forcing. This is a good way to make sure where the signals are consistent with human activities. So, this is another way to show. This is called SPM, corresponds to Summary for Policymakers. So, a IPCC summary document is provided from so called Assessment Report 5, which was released in 2014. The next one, Assessment Report 6, will be released in 2021, every 7 years. Again, all the models like this, newer versions with improvements, more systematic knowledge added to what we knew before, and so on and so forth. And you can wait for this report to see how things have changed. So, before that there was an 4, there was special assessment reports 1, 2, 3, and so on. So, this is now showing the same thing as the observed with its uncertainty because we do not have global coverage. Greenhouse gas forcing, there is a larger uncertainty. Other anthropogenic forcings, including things like aerosols, albedo change because of land, etc. And the combined anthropogenic forcing is definitely large enough, and the uncertainties are not able to explain anything other than what is the observed warming. So, the natural forcings are tiny compared to the anthropogenic forcing, and the natural internal variability due to El Niños and PDO and NAO has been much smaller than the observed warming. So, this is another way to confirm that at least for the last 7-8 decades, the observed warming is beyond natural variability or internal variability, and the forcing is directly way beyond natural forcing, and it can directly be related to human activities. So, that is detection and attribution. Detect a signal that is above the natural variability, you have to go back and attribute the causes for that detected signal, and this is how you do it. There are many more details when you get into other issues that we will see soon in terms of changes in rainfall and so on, which becomes a bit harder, but nonetheless this is how the basic concept works. We looked at the increased number of profiles in the ocean, the atmosphere, land temperature, so on and so forth, satellites, ships, the floats and buoys, etc. And they are now becoming quite good at determining where in the ocean and how in the ocean the heating is going. As I said, you can take the volume of the ocean, increase the temperature by 0.1 degree, compute the calories or kilojoules or whatever unit of energy you want to see what that amount of energy corresponds to with respect to, let us say, the total energy production over the planet, and that is pretty massive. So, here it is in 10 to the 22 joules, the change in heat content of the oceans. So, 0 to 700 meters, since about the mid 1970s, it began to increase fairly rapidly. It was below the climatology we have defined before that, and 700 to 2000 meters also is increasing, and when you combine land, ice and atmosphere, that is a very tiny fraction compared to what is going into the ocean. You have said this already several times, more than 90% of the global warming heat is going into the ocean, and it is penetrating deeper and deeper, and obviously you know that there has to be patterns of warming, as we will see, because where the waters are sinking in the North Atlantic and off Antarctica, Ross Sea, Weddell Sea and so on, that is where a lot of heat can be taken down along with the deep water formation as well as CO2 and so on. Nonetheless, tremendous energy is being stored in the ocean. Ocean has a high heat capacity, it is deep and it warms slowly compared to the atmosphere, but this also means that the energy is not escaping to space, it is all still within the system. So, over long periods of time, you have to see what happens, because warmer ocean can of course increase the amount of humidity in the atmosphere. What will that do to rainfall, to hurricanes, to the monsoon? What will it do to sea ice, land glaciers, ice sheets and so on and so forth? Those are the more difficult questions. So, with the increased data in more recent periods, we are now able to show that the uncertainty in our estimates is beginning to narrow down. So, we have more and more confidence, because the number of observations is increasing, that the ocean is taking up heat, especially in the upper ocean, and the deep ocean is also taking up more and more heat, and that still remains much larger than the atmosphere, land and ice. So, I think obviously is part of the energy that is being lost. So, when we look at the global warming ups and downs, those energy losses have to be also considered, as I already said. So, this is again detection of signals, and we have already convinced ourselves that this is related to anthropogenic forcing. So, here it is showing again the Earth's average temperature since the 1970s, and as I said, there is an argument that the warming rate has flattened since the 1998 El Nino, but after the 2015 El Nino, the question now we are all watching very eagerly is whether warming is going to accelerate back again, because of the canonical or East Pacific El Nino 2015 warmed very heavily around Galapagos and off the coast of South America. So, no more heat being taken up by the ocean like it did between 1999 and 2014. So, this is showing the map of ocean temperatures from 0 to 700 meters. You can see the Kuroshio, the Gulf Stream, Labrador Sea, Gin Sea have all warmed up with significant warming in the Southern Ocean, and of course penetration of heat is clear in latitudes where the deep water forms and in the regions where there are gyres, because we said there is upwelling here, whereas in the gyres there is downwelling or convergence. You can easily see this. If you have gyres circulating this way, you put this will be pushed to the right, this will be pushed to the right. That means water is coming to the middle and it is being pushed down, which means there is more warm water. So, the sea level will be higher. When you upwell, cold waters density is higher, so the sea level will be lower. So, I did not mention this before, but during normal times cold temperatures here, warm temperatures here means there is a difference of sea level of 50 centimeters going from near Galapagos to near New Guinea, and on the other hand going from near the equator to the center of the subtropical gyres, there is an increase of almost 2 meters of sea level rise. I am saying that because the trends in sea level we are looking at are in the order of millimeters and centimeters, but these are the mean level differences. Sea level is on top of that. So, it is like you have a uphill going from there to there and there to there, but on top of that you are increasing the slope of the uphill travel. So, that is why you have warm waters going down in the subtropical gyres, where you can also see that convergence means warm waters or temperature contours are going down, whereas where you have upwelling, temperature contours are going up. So, cold water is coming closer to the surface. So, the ocean dynamics is always important for how the heat gets taken up, where it gets taken up, and how it gets redistributed, because it is not the slow diffusion through the water that happens from the surface. It is the dynamic movement of the heat that is much more important. Something to keep in mind. So, every time we look at these kind of global mean signatures, we should go back and look at the maps. We will do the same thing for temperatures as well in a minute. So, here is the cumulative sea level change since the Industrial Revolution in inches. You can see that the global mean sea level has increased close to 10 inches, that is over 22 centimeters. Not small, but again you remember this is the global mean. Nobody lives in the global mean sea level. The sea level, because the ocean gyres and upwelling change and the sea level changes, the dynamics of the ocean also changes the sea level differently. So, if you have global warming, then there will be some regions which will rise and some will rise faster, and some will actually sink and some will sink faster. So, especially if you are a small island state like Maldives or Fiji or the Caribbean, you have to be very sure what is happening to sea level rise around your island and in your backyard. Okay? But more importantly here, it became obvious in the 1980s that measuring sea level will be one of the critical tests of global warming, because ocean takes up heat and sea level is a good measure of how much heat is going into the ocean, because the ocean takes up heat and expands and produces what is called thermosteric or steric rise. This is different from the sea level rise due to the glaciers melting. And glaciers melt, the water is distributed into the world ocean, that is called eustatic sea level rise. It is called eustatic because where the ice is sinking, growing and melting, the land will be pushed up and down. So, there is a sea level change because of that. Those adjustments of continents are called isostatic, they are local. It is like a ship, you load with cargo, it goes down a little. So, the level against its outer body changes, that is local. So, isostatic. So, you should, there is a separate module you can look up, isostatic. So, isostatic is just the continental adjustments and relative sea level change. So, it is called isostatic adjustment. Eustatic is when you release the melt water into the ocean and it gets redistributed, and steric or thermosteric is because of the warming and also because of the fresh water changes in evaporation, precipitation, salinity and so on. Thermosteric. Okay. Coming back to the satellites basically were designed to go up in space and shoot a laser at the surface and measure the time travel back. So, the satellite is sitting up here, the ocean is here, it shoots a laser, it measures return time, but also calibrates against land. There will be a receiver. So, you can use these differences in travel time to measure sea level changes of a few millimeters to a centimeter. So, the satellite is sitting almost 1400 kilometers up in the atmosphere, way up. It is able to measure sea level change with that accuracy. Remember, there are lots of waves, there are tides, there are these sea level changes from the upwelling region to the warm waters and so on. It can take out all those things and measure sea level change. So, you can see here the sea level change since the satellite launch in 1992 is larger than what is estimated from tide gauges. So, these are coastal stations on all the continents on the planet, and the satellite is essentially saying that those tide gauges on the coasts are measuring slightly different rate than the satellites. Obviously, there is a lot of work to see why they are different, but you can see that the sea level rise is also accelerating just like the global warming. So, that is the cartoon of the satellites. It's called altimeter ranging. There are a lot of details. So, the gravity of the earth itself changes as the mountains in the ocean increase the gravity. For example, as the glacier on Greenland grows, the local gravity increases, so that pulls the water, and when the glacier melts, that gravitational pull is reduced, so the water sloshes back. So, along the coast of the US, for example, because of the reduced gravity, there is some increased sea level which is just related to this sloshing back. Those are the kind of details. But the main point I want to make here with this map as opposed to this global mean is that, as I said, nobody lives in a global mean sea level. So, the dynamics produce different regions with different rates of sea level rise in terms of millimeters per year. The average increase is around 2 to 3 millimeters per year everywhere, but there are where it is much higher and there are regions where it is much lower. So, this is kind of the hot spot where the warm temperatures are, and they are warming and sea level is increasing, and Kuroshio is showing a signal here, whereas the changes in meridional overturning circulation and the thermohaline circulation are showing a different signal here again, just as the warming, and the Indian Ocean is showing a different signal, because as I said, the warming here, basically the deep water is coming into the Indian and Pacific Ocean, it is going out of the Atlantic. So, the Atlantic gets surface water coming back, whereas these get deep water coming in, and that water has to go out. So, this water goes out, as we remember, the thermohaline circulation and so on. So, put all together, you have a story that some of these islands here, Fiji, Vanuatu and so on, are probably highly vulnerable. Same for some of these Caribbean islands, because the sea level is rising quite rapidly, whereas some of the islands here, Seychelles, Reunion, Maldives and so on, the story may be different. So, we have to be very, very careful how we track sea level change. There are some poster children for sea level rise, and the Mediterranean is one of them. So, this is Venice, which is famous for its natural inundation. The land is sinking, and they have been taking out water and gas, which is accelerating the sinking of land. By the way, wherever you mine groundwater and natural gas or petroleum, that tends to sink the land. So, the relative sea level rise happens because the land sinks, and they also get these winds coming from Africa towards Italy, and when there is high tide and the winds are blowing from the south, they get what is called aqua alta. So, huge amounts of water inundate famous Piazza San Marco, where you have the basilica and all the famous restaurants where you have classical music and so on. So, people sit there and continue to eat, and the waiters will just come in these kind of rain boots and continue to serve the food. Sometimes the water smells, of course, but life goes on. So, they can well predict when the aqua alta is coming. So, they set up these kind of platforms for tourists to walk around, but you can see people also plan their weddings and have to go through life. On the other hand, the entire city is built on logs, and you can see the same picture from 1741 to 2002. The sea level has been changing remarkably. So, Venice is one of the classical cases where sea level change is fairly obvious and rising pretty fast. So, let's get into precipitation. I will kind of bring back some of the basic concepts here of Hadley Cell and the intertropical convergence zone, because for the models, doing precipitation or rainfall is very difficult. It's quite difficult because molecular scale processes of condensation, cloud formation, rising air, expansion and rainfall are all not very well represented from first principles, represented by using some relations, using observations and so on. That is called parameterization. So, the parameterizations of convection can produce some uncertainties and differences in the models, because some models parameterize convection based on data and or based on data from the ocean or from the Pacific Ocean versus Indian Ocean and so on and so forth. So, there are multiple convective parameterizations, and they can produce slightly different answers because the tropical convection is different than mid latitude convection, land convection is different than the ocean convection and so on and so forth. There are tremendous amounts of details which we won't get into, but we will just try to point out that rainfall and temperature are very different in terms of the modeling difficulties, and I will explain that with a nice example of how temperature has a very large scale and rainfall has a very small scale. So, here is the trend in rainfall from 1900 through 2010. So, you can see that there are various data sets like Global Historical Climatology Network, Global Precipitation Climatology, and the Hadley East Anglia's Climatological Climate Research Unit product and so on and so forth. There are different versions of the same product and so on and so forth. And we are showing in the background the El Nino and La Nina as well. So, the lines here are different estimated precipitation anomalies, and you can see that they mostly agree, and they don't seem to show a very clear trend here in the global sense, which would make sense, because if you are essentially keeping the outgoing shortwave balanced, but you are balancing it with a different temperature and different convection, then in some sense the amount of rain must be related to how much energy is being lost. So, overall locally you can increase and decrease trends, but overall the evaporation and precipitation must balance in a crude way. Okay? But the big story is, of course, that these local trends going from the 1930s and 40s into the 50s very different in some products, and in fact here this one has a very small anomaly, but these have much larger anomaly, and same here and so on and so forth. And there are some locals here which are also different in different products. This one is producing much more rapid increase, whereas these are different. So, we will come back and see that the contribution of El Nino again to the precipitation is quite complicated, because as it moves the convection and rising air towards East Africa, South America, East Pacific, from the West Pacific away from Australia and New Guinea, it also has global signatures where monsoon, for example, is typically drier during an El Nino. There are droughts over parts of Africa, parts of Brazil, but there are also in Southwest America, Southeast America, and Chile, Peru, and so on and so forth. So, it redistributes rain globally, which obviously contribute to differences in the estimates, because they could be global coverage or they could be local coverage. So, to understand the rainfall dynamics and how global warming response can get complicated, let us go back and look at some of the basics that we didn't look at before. So, let us look at Hadley cell. We said there is convergence into the region where there is maximum heating. For simplicity, we have shown it as just on the equator. So, heating means warm temperatures, rising air, low pressure, also means the condensation in the atmosphere and lot of rainfall. That rising air hits the ceiling, the tropopause. So, that goes poleward, and remember there is also a zonal circulation which is related to El Nino that we looked at. So, that is the Hadley cell. What does the Hadley cell do? Basically, it has a seasonality associated with it, as we will see later on in the next animation. So, the circulation basically includes the northeast trade winds and the southeast trade winds. Here is now the intertropical convergence zone where the maximum heating and the maximum convergence happens and maximum rainfall happens. And in the mid latitude you have the westerlies, and high latitudes we have the easterlies. So, high pressure pole and air coming out, you add Coriolis and you produce easterlies. So, you go from high pressure to low pressure, put Coriolis and you produce easterlies. So, the convergence between the westerlies, which are actually kind of southwesterlies, and the easterlies, which are more northeasterlies, produces another storm track or a rain band. So, we have two rain bands, one extratropical rain band, mid latitude rain band in both hemispheres. That is kind of the background that we learned, but we look at it in terms of animation. So, where the air sinks, there is divergence. So, air sinks has to go out, just like air converges has to go up, air sinks has to go out, right. So, there you will have high pressure, clear skies, no rainfall, and you will get a jet stream there, upper level circulation, which is very concentrated and very fast. There are dynamic reasons behind that, and where the other convergence is, you get, so this is called subtropical jet stream, this is called the polar front jet stream. So, this jet stream wobbles and brings the cold air south, or it goes north and takes the warm air south. So, you can have rapidly changing climate in mid latitudes when the jet stream wobbles. So, this jet stream is much stronger than this jet stream. Okay. So, this is the upper level circulation. There are reasons why the air is mostly going north at the upper levels compared to the surface, where you have southeasterlies, northeasterlies and westerlies and so on. So, we haven't learned all the dynamics, it is quite complicated, it is hard to do without math, but if you are a teacher who is curious, then there will be references provided that you can look up. As I said, the more you know, the easier it is to explain in simple words to the kids. So, that is the Hadley cell, Ferrel cell and polar cell story. Let us take a couple of minutes and look at the seasonality of the Hadley cell. So, what happens? So, as the sun moves, the entire convergence zone itself, because the maximum heating moves. So, you can see that the Hadley cell and the whole polar front and the jet streams, everything move back and forth with the sun. And if you add the intertropical convergence zone to it, you can see that the whole convergence, and when we have summer monsoon, the land heating and the ocean land heating contrast pulls the ITCZ much further north over the Indian, but there is a complicated story there that we will see when we talk about the monsoon. So, this goes way north, and you can also see that this does not cross into the southern hemisphere here, even though it crosses there and there, it remains to the north. That is because there is more land here. So, the land has low heat capacity. So, the heating of the land creates northern hemisphere to be warmer, plus the Atlantic meridional overturning circulation or the thermohaline circulation is also bringing warm water to the north. The effect is that maximum heating tends to remain more in the northern hemisphere. The pressure centers obviously will also grow and shrink as the ITCZ moves north. The high pressure and the Hadley cell changes appear as changes in these centers, and as the ITCZ move north and the northern hemisphere gets cold, the high pressure gets larger because the sinking motion gets stronger. If you add precipitation to it, then you will see that where the ITCZ moves, you get high precipitation, especially stark contrasts here. So, the West African monsoon and Indian monsoon, for example, have strong rainfall signals associated with the ITCZ coming overhead. So, we have to remember all these things. Obviously, again, where the Hadley Cell sinks is where you have the minimum rain zones and the deserts, and technically India should be a desert, but because of the ocean land contrast and the heating and the monsoon, we actually have plenty of, always facing water shortage. There are other issues that we will look at later on. So, now we have to take all these together and see how global warming impacts each one and how the interactions between them modulates the global warming. So, we will do that when we come back. I went back to this to basically show that the rainfall response is very complicated, modeling the rainfall is very complicated, observing the rainfall is very complicated, how rainfall responds to global warming is very complicated, which means projections are very complicated, big challenge, which means uncertainties in the projections could be high. That is what we have to remember. So, we will look at those kind of details when we come back. See you next time.